as I have told you earlier, we have a three different platform like DSP boards, like your FPGA boards, like your Arduino boards. We have FPGA boards which I have the most and more popularity in your FPGA power electronics field. And if we talk about FPGA, basically FPGA is a wide platform in which we can program our logic, digital logic, in the form of logic gates. We can implement our logic with the help of this reprogrammable logic gates. So it's a different environment from your microcontroller, because if we talk in broad category, the microcontroller based system all are sequential. The programs flow in the form of your assembler, like program counter store the next address of instruction, and it goes like sequential ways. Okay, programs runs in your microcontrollers. But in FPGA, what happens? In FPGA, the data flows in your logics, in your AND gate or OR gate and mux logics. There is no type of program storage. There is a direct linkage of your fuses with your logic gates. So there is no sequential type of circuits. There is the massive parallelism in this type of FPGA. That means there is a type of parallel algorithm you can implement. In a single FPGA, you can create number of controllers which are interconnected in together, but it is working on independently. Because in the case of microcontroller, we have to combine it with the help of some interrupt handler, or with the help of some other techniques, some fault techniques. So it's a basic definition of your FPGA, that it has a large number of cells and we can interconnect with the help of some anti-fuse technology. It's very in the case of, you can say, the large run, it is very easy to produce, because whenever we complete our ASIC design, we can produce our new IC over there. Even all microcontrollers or microprocessors are basically designed on that platform also. So it's a very easy thing to use. It's a simple structure of your FPGA, that how FPGA are interconnected. Here you can see there is a programmable input-output blocks. As in Arduino, we have an input-output pins to assign. There is an input-output programmable blocks which can be assigned as input or output in the same fashion. There is a program logic blocks which can be programmed according to your program. These are the fusible or interconnections. By the help of this interconnection, we can connect this unit to this unit. Okay, so there is no program which is to be burned, which is to be stored. In the microcontroller, what we do, we burn our program in our ROM, and after that the controller read our program from your memory and accordingly works. But in FPGA, there is no program burning. There is directly of data flow. So speed is very, very faster in FPGA. First is the advantage of this. Second one is this: we have a limited clock in your microcontroller based system, like 16 megahertz, like 24 megahertz. But in FPGA, whenever we talk about FPGA, there is a large span of your frequency. Like in Spartan 6, there is a 300 megahertz of we can say frequency over there. So for that, you can even produce your 10 nanosecond pulses. See, if we want to produce a specific output of PWM, or we can say from inverter, you can just go for FPGA and it will give you a specific output of your required frequency, because there is no limitation of your combination of your clock frequency which is associated with your controller or some other processor. So there is a very wide variety of frequency ranges available. You can use clock divider, you can use different frequency on the same platform also. Okay, so whenever we talk about FPGA, there are some prime members in the field, that Xilinx, the Astel is there, Altera is there, and we can see the Xilinx is the most dominant in FPGA area, and Xilinx produce a number of FPGA boards. They are very differently according to your programming method and your interconnection arrangement. They basically difference according to your this criteria. Programmability in FPGA, basically there are two types of programming in FPGA. There is a SRAM, static RAM, or we can use some anti-fuse based programming. In anti-fuse based programming, it is only one time programmable. You can program only one time. It is only used for making a product. Whenever you want to make a product, you will use this one. You have tested your logic, you have done everything, you have done all related document and research work. and you want to make a product, then you will go for anti-fuse based programming technique, and it will be a cheap than your SRAM, because static RAM is always a cost item. So for that purpose, for programming purpose, for learning purpose, we use the SRAM based programming system. Okay. Reasons for choosing the FPGA. There are different reasons for the FPGA, which are really very better than microcontrollers. Like FPGA are very high speed because the controller behaves on a sequential logic manners. But in FPGA, there is a concurrent, there is a parallelism. You can produce a number of logics which are not interconnected, but they are working on the same manner, or they can also get interconnected, but they are not sequential. Okay, so you can understand like that. If you want to use an ADC and it has a 12 channels, so at one time it will only take one channel. After that, it will take two second channel. After that, it will take third channel. But in FPGA, if you connect the ADC, it will can take all the input at the same time, because it have a different controllers. This is the main thing which we talk about, parallelism and sequential. Okay. Next, we have also show you that parallelism pipelining is very most powerful tool of this FPGA. Flexibility, you can add or subtract any type of functionality. Means in the microcontrollers, if you have a given parameters over there, and if you are not using them, then they are waste for you. Actually, you are not using timers, you are not using ADC, you are not using PWM. Then what is the use of that area? Because you are using only few pins and you are paying more for that. But if you go for FPGA, you can design your simple microcontroller, simple different IC, which is only do for your task, which is given on your program. Okay, so we can also reduce our cost, we can also reduce our area, we can also reduce our increase our speed as well as. Okay, so these are some we can say advantage of FPGA. But for understanding the FPGA, we have to understand the logic, we can say the programming language which is associated with this FPGA board. We have to understand that how Verilog works. Basically, there are two types of SDL. SDL stands for hardware description language, and it is generally Verilog and VSDL, very high description language, and Verilog. There are two types of language which are used for your FPGA applications to writing your or your doing your logic to your FPGA. Okay. Basically, Verilog is a easy language, and the syntax are more easier than VSDL. We can use your Verilog very easily, and if you go for behavioral modeling, it is just like your C language. Okay, it is not very hard, because in this case also we have switches, we have a switch case, while we have a if and else condition also. We have a different types of other AND gate operator and OR gate operator. They are always over there. So in behavior modeling, it is very easy to learn. Okay, it is also written over here. It is like just C like. So if you have something knowledge about C, then you can easily understand the Verilog, because it's not very hard language. Okay, so why we use the Verilog? Digital systems are highly complex, and we want to implement this so we can easily do with the help of some behavioral tasks. Okay. These are some advantages. Then what is the advantage of your Verilog? It is basically different from your procedural language. Procedural means sequential languages, because one after one the program will execute, the task will done. But in this case, if you make a module, it will behave. If you make a module in a one folder, then module 1 is working, module 2 is working, module 3 is working at the same time. There is no sequential. All are working on the same time. So speed will be fast, and your output will be much better than of that. Okay. In the case of our inverters, we always want that all pulses comes directly to the at the same time. There should be no sequential something like that. So all the pulses should be come at the same time, and the thing should be of go in this manner. Okay. So that's why FPGA is more popular in that. It's basically a simple procedure design. I will not go in deep of that, because we have a limited time period, but I will show you that how we can produce a easy program for our multi-level inverter. Basically, level of abstraction. Basically, there are 3 levels of programming method. We can say there is a behavior level, there is a data flow level, and there is a gate level. In the gate level, we only design our combination logic designs. In data flow, we write our program in the form of data. Okay. In the behavior level, it is like C-like language. Okay. Behavior modeling. In the behavioral modeling, you see there is a keyword like module. Examples may be any word, whatever you want to put, and your x1, x2, x3, xf. These are your input and output, which is defined, should be in this manner. After this, you have to define what are your input and what are your output. With the help of these words, input will be of x1, x2, x3. These all are one single bit input, and output will be of your f. For output, you have to connect a register. This is a predefined name, that is reg, and we have to put a name, a register for your output. There is no need for creating your input register. Okay. So first of all, we will write module. We will name that program, whatever we are going to use, and we will put the input and output, whatever we are going to use in the starting. After that, we will put a name input, that is a keyword, and here we will put assign your inputs. After that, we will put your output and register. This is your next notation, that is your always at the rate. That means always at the rate x1 or x2 or x3. That means whenever there is a change in x1, x2 or x3, this block will work. The meaning of this notation is that whenever there will be a change in x2, x3, s3, x2, x1, x3, this program will work. In the C, we use the parenthesis, start and end, but in Verilog, we use the begin and end keyword. Okay. It's not very tough to remember. In Verilog, what you will use? You will start begin and end. Start and end for parenthesis. Now, if we write a simple program like if x2 is equal to 1, that means if switch connected to x2 is high, then what will happen? The f should be of x1. Okay, else f should be of x3. If you see closely, it is just a 2 close to 1 mux. Where is incremental? It is equal to. It is not showing like this. No, there is no minus. There is equal to. Let's see what is coming over there. No, it's not possible. Actually, in C++, we put the double plus for the incremental thing. I'm not decrementing it. I'm just comparing it. In if statement, always we compare with 0 and 1s, because always we have defined it as a bit. Let's see what is happening. It should not be like this. It is basically like just if you have a very basic knowledge of C. Yes, very easy. But VSDL is much more typical. So we refer a Verilog for starting purpose. Basically, it's near about 10 to 15,000. It works on your hardware capability on that. If you have an inbuilt ADC, inbuilt DAC, inbuilt UART, inbuilt your different type of functions. I have shown in my project, it's a Wipro based Mission 10X based kit. Basically, it is a cost of 40,000 rupees, and it has inbuilt DSC processor, it has inbuilt DSC processor, it has inbuilt OMAP processor, it has inbuilt Xilinx. Three features are available. Embedded system also, FPGA also, and image processing also. Camera interfacing, ADC, DAC, everything was all there. So cost is basically 40,000 rupees. And we didn't purchase it, we college provide us. Because madam, I also tell you that the college did not allow for taking that kit. Okay. Yes, that why. But in our college, we do such type of things, and we are free to do that. But we cannot move that kit anywhere else because we have a type up with Wipro, and we cannot use it for any personal type of use. Okay. Yes, we have. Yes, we have. We have in Meerut. So this is kit are produced by iWave Technology basically, and they have a collaboration with Wipro, and Wipro manage the programming of the FDP on different type of competition over there on the same platform to understand
what
that.
are the main core research areas you work on with Wipro?
No, Wipro is just providing a platform for students to understand embedded system,
Okay,
embedded system, FPGA technologies or DSP. They want some different projects from undergraduate level students so that they can enhance their skills. Basically, the purpose was that only.
compared to something research and what is it?
Yes, yes. But we may use for different type of application also. But if you want to purchase your own FPGA kit, it is not near about 5 to 6,000. It's also available. Spartan 3A kit is near about 5,000 rupees. But the functionality will be reduced. You will not get a lots of pins. You will, although you can get lots of pins, but other functionality will not be there. Maybe there is not on-chip ADC, DAC, and other features over there.
Specifications will be ready.
Yes, yes. But for Minium, you can start very easily. It's near about the area of that kit. I have one kit in my college, near about just twice of this Arduino board. It's a very simple kit.
So if you compare both the software, you talk about FPGA and
FPGA. FPGA is not a software actually. Software is Xilinx IDE.
Xilinx ID is here, but
Yes.
you collaborate with FPGA.
I tell you, microcontroller is a word which associate with your IC. Okay. Arduino IDE is a software. Language is C.
Yeah.
Same comparison. FPGA is a technology. Like microcontroller, FPGA is a technology, and Xilinx IDE is your comparison with Arduino IDE software. Language is compared with your Verilog. This is your basic comparison. So FPGA is a technology basically, we can say. Microprocessor is a technology-based IC, different architecture, different programming methods. Likewise, FPGA has own boards. So programming we can say Verilog, but it's very easy. I will show you that it's a very 5 to 6 10 minutes. You will understand that how you can produce your own inverter with the help of this simple technique. You need not to go to in deep of your Verilog. You should not need to worry about how Verilog will work. Nothing. You have to just use that code only, and it's very easy.
But Arduino is much more easier, I guess.
See, if you want to compromise your performance, then you have to compromise with your cost. Okay, if you want your performance higher, excellence, then you have to raise your cost also. If you want a less performance, then you can manage with your less cost. That means Arduino. That is the basic difference. Suppose if you want to make a DC-DC converter and you design yourself, then you want, I need a 19 kilohertz frequency because I have an inductor, I have a capacitor for that, I have everything algorithm for that. But 19 kilohertz cannot be produced by this Arduino board. Okay.
Main thing is this limited.
Main thing is fixed range.
Fixed range is there.
Okay, if you are okay with 31250 kilohertz, then you have to change your hardware part. Then you have to produce your own inductor. Then you have to produce your own capacitor according to that, because everything is associated. If you go in deep your DC analysis of your DC to DC converter, what is the range of inductor should be there, capacitor should be there. They are all interrelated with the help of frequency. When I change the frequency, everything will be changed. Output will be may differ. We have basic knowledge of FPGA, and we were talking about your behavioral modeling of Verilog language. Now we just move on further. I have told you about the PWM generation. I am just going to focus on this major area. We have a PWM, like we have to make a counter which will start from one initial value and go to some predefined value. Okay, and in between that we have to put your threshold value over there so that we can produce a different type of PWM wave. How we will do it in our FPGA, or we can say in Verilog, I will show you. Suppose we have a crystal frequency of 100 megahertz which is connected to your board, and the clock period will be like 10 nanosecond. In our case, Spartan 6, there is 100 megahertz of crystal, and we can produce a minimum pulse of 10 nanosecond. Okay. Now, if we see the one count or one tick will be equal to your 10 nanosecond. If we put over here 2500, that means it will be of 25 microsecond. I'm going to produce a frequency of 40 kilohertz. If I'm going to produce a frequency of 40 kilohertz, I need a time period of 25 microsecond. Fine. Now, I have to map again this value to your input value, because input we are going to get with the help of some ADC or with the help of some 8-bit switches in the form of 0 to 255. So we have to map these two values accordingly. So here in this hand we have a 2560 value, which is counter value, and we have a maximum switches value, or we can say potentiometer ADC value is 255. So we have to put a scaling factor over there, SD. Okay, we have to put a SD over value over there, so that we can compare this value to this value. We can map actually. So according to this program, I have made a program of PWM generation. Like, there will be a module, keyword, and PWM will be your name of your project. There will be a clock. Clock will be for sequential logic circuit. So we have to put this clock word over there. So, after that, PWM will be your output and SW will be your switches. We are going to control our PWM output with the help of 8-bit switches. If we change our 8-bit switches value, the PWM value should be changed. Now we have taken the SD parameter as 10. If you go back, you see, if I put over here 10, it will just like your equal to 2500. Fine. So SD is just like your 10. Now we have defined clock as input, because always clock as input, it is inbuilt, but it's still we have to define it as an input. Now we have a switches in 0 to 8, that means 0 to 7. We have 8-bit switches, so we have to put in this manner. Okay, if we want to put a 3-bit switch, we will put 0 colon 2. Okay, like this. Output will be of your PWM output. Okay, so we have need a register associated with it. We need a counter to increment the value from 0 to 2500. So we need a counter. So we have taken a counter of 16-bit. Let's suppose. Now we start from here. Always at the rate positive edge clock. That means whenever the clock has positive edge, this function will work. At every clock, this function will work. That means at every clock, the counter will increment. Counter will increment and everything will happen. Whatever you have written from begin to end, everything will happen in that clock. Okay. Counter is equal to counter plus 1. Whenever the counter will increment, clock will there, the counter will increment. Now we are going to compare this counter with our switches value. Now this switches value come from your 8-bit switches, and SD parameter will be multiplied. And if it is less than, if it is greater than counter, the output will be 1. PWM is equal to 1, like in this form. And if else, output will be of 0. Until the switches or SD value is greater than counter, the output will be 1, otherwise it will be 0. You can also change this value, because the T on and T off make your duty cycle. Then you can go for T off divided by T on plus T off, or you can go for T on divided by T on plus T off, whatever you want. So according to this, we put 1 or 0, 0 to 1 over here.
What is implication of PWM equal to 1? Can you show me?
It is high signal. Yes. 0 is low. Okay, na? So this, if counter is greater than 250, so counter should be 0, because we want to make a counter from 0 to 250. So whenever the counter will increment from 250, it should be 0. So we will get a limited frequency, or we can say we have a limited time period. Now when we run this program, we see a different type of output pulses over here. Yes. Let me, now it is okay. It is again minus, or it is equal to, it is okay. You have a question about that figure. It is equal to.
It comes now equal to, but before slide.
Yeah, it was a problem of some other thing. So it's an implementation of PWM, or we can say FPGA. I have a video which we will show you that how we can use this. This is our window on which this function is working, like Xilinx is working. Basically, it is working on Ubuntu software, that is your open source software. And we have PWM.xic stand for new project, which is already written. You can see over here the code which I have shown you in this. It is written over there. Okay. We do some steps. After that, we produce a XSVF file and we burn it on your hardware. It's a basic simple steps. It's a not very hard steps to understand. So I am just going to show you some implementation part. Okay. So after loading this program, what we will see, we will have a this type of waveform. Now, if we change the switches value, it has an inbuilt 8-bit switches. If we change our input value, like if we change our input switches, then what will we have? We should have a different PWM output. Fine. Now we have changed our input value like this, and by the help of DSO probe, we can see the output has been changed. Okay. Again, if we change our input, again the output is changed. It is showing your side also, same thing. So whatever the switches will be there, the output pulses will vary accordingly. So this code will be useful for your DC to DC converter controlling very easily. Okay. Now we have a last code, that is your 3-phase inverter code. See, this is your inverter code, which I have implemented in our 3-phase solar inverter. I am going to show you that how I implemented. It's very easy. It's not very tough. Now you will see, module is your keyword. Inverter will be of your name. There will be a clock input, and we have a different type of pulses. I have put the 3 group like S1, S2, S3, and S1, S2, S3, like different types of all whatever the signals are there. I have put over there. Gate pulse shows the prime 6 MOSFETs, and other R shows the these arms. Okay, these are all, everything is there. Now it's a simple code. If counter is less than this value, I have make this code like according to your waveform. The waveform work like T1, T2, T3, T4, T5. I just combine them with the help of a counter. If counter start from this and end to this value, it is like 388.88 microseconds. So it will, whenever the counter will be in this range, the output should be like this. Counter will be in this range, output should be like this. The counter is in this range, output will be like this. So according to your table, you can implement this code very easily. We will only consider about the T1, T2, T3, T4, T4 time. This time will be there, the code should be like this. You can see the different values will be given to your pulses, to your switches, MOSFETs. So it's a simple technique by the help of which you can easily generate different type of inverter pulses. Any type of inverter pulses you can generate with the help of simple notation, like you will start only begin, end, and you will put the different status of that, 1 or 0 accordingly. In this case, you can see only 3-bit will be 1, 2 1 is there, and 1 is there. So 3 switches will be 1, and other will be all will be 0. So with the help of this code, you can easily do this, and after 1999.8, this value, the counter should be of 0. That means 20 millisecond, after 20 millisecond, the counter again should be of 0 value. So this is my objective to show you. Okay, there is a DC to DC converter which was basically implemented on this. I'm just going to show you this Simlink value. You can also simulate the code you have generated before implementation of your hardware part to in the inbuilt ISC tool. The ISC, the Xilinx ISC toolbox have an inbuilt simulator in which you can show your pulses. You can see there is a pulses which I have obtained from our we can say simple logics, and these are equally to your logic designed by your Verilog program. Okay, so before implementing, as we done in Proteus, okay, we have done in Proteus for simulation purpose. In the Arduino, in the FPGA Arduino, this software Xilinx ISC has an inbuilt simulator. So you can, before you go for implementation, you can check your pulses over there. So it's a simple process by which you can compare logic to your implementation part. And if everything is okay, then you can implement this to your FPGA board and to your basically your main inverter. Okay. After this, whenever if you done the simulation, you will get a block which will be called like inverter, and it has a one clock input because it has no input. Inverter, it has no input, but output will be like, will be shown like this. If you double click on this inverter, you will see a large number of gates, mux, LUTs in this inverter block. It is for implementation part. It basically map everything with the help of some software. It has an inbuilt software capability which map your language to your FPGA board. Okay.